Welcome back. In the last video, we talked about fit. We have fit refers to the amount of the tightness or looseness between mating part. There are three type of fits. We have currents, interference, and transition. So last video we talked about current feed, interference feed, transition feed, shaft limit, hole limit, allowance feed, current feed, interference feed. Uh, when we talk about the design size, now we're going to continue on to talk about the maximum and minimum sizes. So in the drawing, some drawing that define what is the maximum and the minimum are acceptable. The concept of maximum and minimum sizes, they are the sizes between which the actual length and diameter of the produced part must fall. After all machining processes have been completed, the inspection department will check the part. If the actual produced size fall within the established maximum and minimum sizes inclusive, the part will be passed as usual. If it's smaller in any dimension than the minimum size, the part will be swiped as waste. If it is larger in any dimension than the maximum size, it may be salvaged through additional machining. So what it is they define with maximum and minimum allowable to manufacture this component. Let's say this shaft and this hole. If the max the max is 3.01, if if you create something that is greater than 3.011, that means this may be salvaged through additional machining. So we're gonna throw them away, gonna recycle it, and then do other machining. So if it's less, it's not gonna do anything. Then the part will be scraped as weights. Location limit. Location limit is how limits are applied to location dimension, and location limit will be accepted if the central line of the hole fall within the limit shell. So if it's fall within the limit shell within this location, then it's acceptable. Depend how the circle is. If the circle fall within this dimension, then the product is accepted. Design location. The design location is the location the engineer actually wants. Is theoretically ideal location of the feature. The dimensions shown on this figure are the design dimension, sometimes referred to as nominal dimensions. The specified tolerance is applied to this nominal dimension to determine the upper and lower limit for locating the feature. So you want to locate this feature, so you're gonna have to define the this nominal dimension and then determine the upper limit and lower limit in order for the manufacturer to manufacture. If it's greater than the limit, and then we're gonna apply the same idea is to anything is larger than the allowable location, then we may have to salvage it. So maximum and minimum location. How do you determine maximum and minimum location? Here's the rule. All tolerances should be given as large as possible without interference with the function of the part in order to keep costs down. Closed dimensions are expensive. So what does it say that all dimensions should be given as large as possible without interfering with the function of the part in order to keep the cost down. Closed dimensions are expensive. That means the tighter the fit, the more difficult the part is to manufacture. The most difficult the part is to manufacture, the more it costs to manufacture. Therefore, engineer should never assign a tighter fit than is absolutely necessary for the part to properly the function. So that means we're going to have to establish what is the maximum minimum can this hole be located, and we're going to have to define this is the minimum you can go. If you manufacture something that is less than this location, then your part is not gonna fit in. This is the actual dimension, but if you create something that 0.990 and is acceptable, but if it's less than 0.99, that means we got problem with the location. Point won't fit in. So same thing applied to vertically and also horizontally. Have to define the location of that hole. So to determine that, you have maximum material condition plus tolerance, the whole equal to least material condition. So we have a clearance fit and the interference fit. For the clearance fit, simply use MMC whole, maximum material condition whole, minus allowance equal to MMC shaft minus tolerance to get least material condition the material. So same thing applied to interference, MMC hole plus the allowance, shaft plus tolerance, and then equal to least material condition for that shaft. Matching part, so the part A must fit over to part B. This is part A. This hole must fit into this shaft. So you want to make sure that before you begin to manufacture this item here, you're gonna have to calculate this maximum allowable tolerance so that the manufacturer won't create something that is greater and then waste up all this material because it won't fit into this hole. So part A must fit over to part B. It is critical that features on mating part are to be located from the same datum. As shown in the figure, some transitional factors to consider when planning dimension for matching part are the length of time the part are to be engaged, the speed at which mating part will move after assembly, the load of the part after assembly, the type of lubrication used if lubrication is necessary, the average temperature at which part will operate, the level of humidity during operation, the material of which part are made, the required functional lifespan of the part, the capability of machine tool, and the people that operate them in the manufacturing part, and of course the overall cost of the part. As you can see from this matching part here, the tolerance is only plus minus 0.015. If your error happen to be, if your tolerance happen to be either greater than this number or less than this number, then this hole may not fit into this shaft. With that, we're gonna go on to the next video to finish up the standard fit.